Okay, hello. So what we're going to be looking at is chapter 1. And the first part of chapter 1 goes through some measurements that you don't actually need to memorize all of them. You just need to know mostly about the first one. But it is amazing that ancient people knew much more than we gave them credit for when we were younger. Anyway, so we're going to be looking at a little history of scientific measurements. We're going to be looking at, in the second video, we'll talk about the scientific methods, the attitude, and so on. All right, so let's go look at history of science. Now, one thing is that science has advanced amazingly. I like these two pictures because they show some huge contrast. You have the alchemist sitting here in his lab all alone, whereas a lot of scientists work in large groups. My husband is at Fermilab, and he works with other scientists from all around the world, hundreds of scientists on a project. And the thing is that what has really been amazing is that the science has been able to be confirmed and handed on. We've built layers upon layer of scientific knowledge. And so that has led to all these amazing things that we have, like your cell phone, like this video, your computer. And it's not stuff that is kept hidden. So that was one of the old ideas, was that you kept your knowledge to yourself because it might make you rich or make your family rich. But instead, what we have here is nowadays scientific knowledge is available across the world. Other scientists are supposed to test it and check it out and then build upon the knowledge from others. Anyway, so we're going to be talking about some scientists during this class. We're going to talk about Aristotle, who for physicists was not a very good scientist. In fact, he didn't experiment, which is terrible. But he was a good observer of the natural world. So a lot of biologists still consider him the founder of biology. Archimedes, great engineer, the guy who came up with the mathematics for the lever and did a lot of other math. Now, Galileo is who we consider the first true scientist. And if you look at those dates, the Archimedes 250 BC, Galileo 1530 AD. Okay, so what was going on in between there? Well, of course, Rome fell, and what happened was a lot of knowledge was lost. And in Europe, they had what are called the Dark Ages, where knowledge was not being tested, and there was a lot of superstition. And so the Renaissance was coming out in the 1500s. Galileo was part of the Renaissance. And it wasn't just a Renaissance in painting or sculpture or music or architecture. It was a Renaissance of science also. No man considered himself a whole man, okay, a Renaissance man, unless he also was interested in science and math. So anyway, so Galileo was our first true scientist who followed the rules of experimentation and publishing. And so he was the one who all the other scientists built their knowledge on. So Robert Boyle there, he was instrumental in getting chemists to follow the ideas of measurement, writing things down, describing your lab equipment. Then came Isaac Newton, and Newton picked up where Galileo left off in terms of motion and optics and things like that. And then we've got Antoine Lavoisier, and he was another one who was a builder of the rules of chemistry. Okay, so Galileo and Newton for physics, Boyle and Lavoisier for chemistry. Anyway, the idea is that knowledge builds, and true knowledge makes a firm foundation. So that is why this shiny picture here with all the giant chemicals and cool electricity going on, is sort of our world. We have amazing stuff around us all the time. And usually at this point, I'll ask a class, how many of you would be dead if not for science? If not for medicine, for instance? And usually about 1/3 to a half of the class acknowledges that they probably would have died. I know I would have been dead the day I was born, but a blood transfusion saved me. And since then, I could have died 2 or 3 times. So yeah, science makes a difference in lives. Okay, so let's go look at the first experiment we're going to talk about here. Now, this is an experiment that was performed in 235 BC. And it was performed in Alexandria in Egypt by Eratosthenes, who was a Greek. Now, if you know your history, usually I'll ask the class, what were the Greeks doing in Egypt? And somebody usually knows the answer. Well, Alexandria, the city, was named for Alexander the Great. And he founded the city after he conquered Egypt. And as usual, he left Greeks there to rule over the people. And so that's what happened in Egypt too. And so Alexandria had a lot of Greeks there, and they built the famous library, and that you've heard about, that burned down. And so the thing is that there was a lot of knowledge in Alexandria. And the library wasn't just a library, it was also a school. So people would go there to study. Okay, so anyway, and by the way, Cleopatra is descended from the Greek rulers who Alexander put in place. So she was more Greek than she was Egyptian. Okay, so anyway, so Eratosthenes measured the size of the Earth. Now, looking at this, you'll see that Eratosthenes knew that the Earth was round. He wasn't saying the Earth was flat. He was acknowledging already that the Earth was round. A lot of people know that the Earth is round, and throughout history, a lot of people have believed that. For one thing, the shadow of the eclipse, the shadow of the lunar eclipse, is the Earth's shadow, and it's round. So anyway, so you can actually see that the shadow of the Earth is round. So no flat Earth. Anyway, so what he did though was he had heard that in Syene there was a well, and this well was very, very deep and very, very narrow. And on a certain day of the year, sunlight went completely down this well and reflected off the water deep, deep, far below. And so the thing is, he thought he could use that because he would know on that day that the sunlight was coming vertically and perpendicularly to that well. So on that day, what he did was he measured the shadow of a pillar in Alexandria. Okay, so let me draw that for you, a little bigger. Okay, so here's the planet Earth, part of it. And the idea is that the pillar, since it would be coming straight up from the center of the Earth, right? Because you always put your pillars upwards. Okay, so the pillar would be heading towards the center of the Earth. Now, the other thing that was going on was the well. And the well over here, the deep well, also was pointing towards the center of the Earth. And so the idea was that sunlight would be coming from the sun. And the cool thing about sunlight is by the time it reaches the Earth, the rays are pretty parallel. Because the sun is 93 million miles away from the Earth, then any rays that are going to reach the Earth are pretty close to parallel because they had to be heading in the same direction. So the rays of the sun are parallel at that point, and one of them was going down the well, and one of them was causing a shadow on the pillar. So the size of the shadow meant that if he knows the height of the pillar, then he could figure out this angle. So he could figure out an angle there. And the thing is that if you remember your geometry, when you've got two parallel lines and they cross another line that's diagonal to it, the angles here equals the angle here, right? It's the same angle. And so why was that important? Well, now he knew the angle that the distance between Syene and Alexandria subtended. He knew that this distance represented this much angle of the Earth. Okay, so that was the idea. This was the distance, and he could now relate it to a part of the Earth's circumference. Okay, so he figured out that there was 7.2 degrees in that angle. And the distance from Syene to Alexandria was, I believe it was 500 stadia in your book. They actually give you a number. And that 5,000 stadia. Okay, so 5,000 stadia. So that had been carefully measured. And so the idea is that you could relate that distance was one segment of the circumference, just like the angle, 7.2 degrees, was one part of 360 degrees. So those two things can make ratios, and Greeks love to make ratios. They're the one who came up with the word. So anyway, so they would make a ratio out of it. And because of this, because they knew the 7.2 degrees, they knew 360 degrees for a complete circumference of the Earth, and they knew the distance from Syene to Alexandria, there was only one unknown, the circumference of the Earth. And so Eratosthenes actually measured the circumference of the Earth, and he was so accurate, he was within 5% of the actual value. Amazing. Okay, so this was known in 235 BC, how big the Earth was. Now, Columbus, you may recall, tried to go around the Earth. And when he was trying to persuade Queen Isabella to fund him, one thing is he said, well, this is how many days it should take for us to get to India, because that's where he was headed, was towards India. And so he would tell her that, it's this much distance that he had calculated. His calculation was off by almost 30%. Now, some people think that he kind of kept picking numbers that would make it smaller because he didn't want it to make it larger, because nobody would sponsor him for the actual trip to India. His people would have starved if they had not found the South America and the islands and North America in the way. So that would have been in the 1400s, right? 1492, he sailed the ocean blue, and so that's 1700 years, and Eratosthenes' measurement was forgotten, and Eratosthenes' measurement was so much better than Columbus. Okay, but the Greeks didn't stop there. What they did was, now that they knew the circumference of the Earth, they figured out the diameter of the moon. And this had to do with the eclipse. When the skies were much darker, you could see the stars in the eclipse much better, especially the eclipse of the moon. And they knew that even though light rays are almost parallel, the sun is so large that you can actually get light rays from the top and the bottom of the sun that give an angle. And so what happens is that you get a tapering shadow. Okay, so when it's just one small part of Earth, 5,000 stadia, the beams are almost parallel. But when we're talking about the moon, then you start to see that tapering distance. The moon is 250,000 miles away from the Earth. And so that's a big distance. So the taper shows up, unlike with the pillar. You're going to see a difference between the shadow here. So it matters that the beams are not exactly parallel. Anyway, so here you get a tapering shadow. And they knew that, just like our eclipse that we had in 2017, you had to drive down to the right place to see it. Because by the time the shadow touches the Earth, it's very, very small. It's only, was about 75 miles wide that you could see the total eclipse in. And so you had to be in the right place to see it. So if you stayed up here in upper Illinois, northern Illinois, then you could only saw a partial eclipse. So the ancients knew you had to be in the right place, that the shadow tapered. And they calculated that when the moon goes through the shadow of the Earth, that's a lunar eclipse. Okay, whereas this was a solar eclipse. During a lunar eclipse, they knew that it took the moon would go 2.5 times its distance still in the shadow. So that meant the Earth's shadow was 2.5 times wider than the moon. So what they figured out was that the Earth's diameter was 3.5 times the moon's diameter, because you've also got one diameter of the moon that tapers down to almost nothing because of the tapering. Okay, so anyway, so if you add in that tapering effect, then what happens is that it's 3.5 times the size that the Earth is. So anyway, so including that, they could figure out what the moon's diameter is. So we already knew the Earth's circumference. So from the circumference, we can get the diameter. And now we can get the moon's diameter. Okay, but they didn't stop there. They kept doing more calculations. Now that Aristarchus had the distance to the moon, what they did next was they could figure out the diameter of the moon. And you could do this yourself. This one's pretty easy to do. You don't have to wait for an eclipse or anything. You can just hold a coin up to your eye and move it till it exactly covers the moon. Okay? So next time there's a full moon, you could try this. And then what you would do is measure the distance between your eye and the coin. Okay, so that would be the distance to the coin. And then the idea is that the distance to the moon, well, you can figure that out by similar triangles. What you've got here is a small triangle made by the coin and a large triangle that has the same angle made by the moon. So they have the same angle, and therefore their sides will be ratios of each other's. And so the diameter of the coin and the diameter of the moon will have a ratio. So what do we need to know? Well, we already have the moon distance. That was already figured out. We have the coin distance and the coin diameter. So the only thing we don't have is the moon's diameter. So they set it up as a ratio. They found out the ratio was 1/110. And so in other words, the moon is 1/100th. Basically the diameter of, the distance to the moon. Okay, so you've got a homework problem that has something to do with that. And so anyway, so now they knew the diameter of the moon. Okay, so what's next, these clever people? Well, Aristarchus next measured the distance to the sun. Now that he knew the distance to the moon, so he knew this distance, okay? And the other thing is that he knew that the reason that you see a half moon, which is also called a quarter moon in the sky, it's a quarter of the way through its cycle. So in other words, the full moon position is over here, the new moon position is over here, and then you get a quarter moon, which looks like a half, in between those two. And so anyway, so that would happen when the moon distance to the Earth, the direction to the Earth, is perpendicular to the direction of the sun, so 90 degrees. Okay, so using that, you could, during a quarter moon or half moon time, you could go out and measure the angle to the sun. So that would be X here. And now you can use trigonometry, which the Greeks invented, which is all about ratios, to figure out the sides of the triangle. And so you can measure the distance to the sun from the Earth. So anyway, so you've got, so they figured this all out. Now, by this time, the numbers have been used and reused, and since there were approximations, it was down to 1/20th. But the thing is, it was still an amazing achievement because the distance was so far. I was saying that the distance to the sun is 93 million miles. The thing is, 1/20th of that would still be 5 million miles. And so the thing is, nobody had any idea the sun was so far away. You've probably heard all the myths about the chariot of the sun that would pull the chariot around the earth, right? The sun around the earth every day. And if you see Egyptian folklore, they have the stars and the sun held up on the back of the goddess, so she's holding it up. So they didn't think it was very far away. 5 million miles? That's pretty incredible. Anyway, this is some of the knowledge that was lost over the centuries, partially from burning and things like that. And then gradually over the years, some of this was recovered. Some of this went into libraries in faraway lands and then slowly came back to Europe and Greece and from Egypt. Anyway, so the thing is that the knowledge was lost. Sometimes it was in a written down, and then people would reuse the material, so they would erase the old stuff, but you could still see it underneath. Anyway, we finally figured out that the ancients were a lot better than we thought with their knowledge of the world, and much better than Columbus. So anyway, measuring the size of the sun, like I said, you could do that yourself. This is another way to do it, where again, these would be two similar triangles where you would be looking at a sunspot on the ground, so like this, or on a table, and you could make one with instead of leaves, with a hole in cardboard, and then you could have ratios again. So you could figure out the distance to the sun from the ratio. Okay, so anyway, that's the first part of the chapter. And I'm going to click this off, and then I'm going to start the next part. Okay. Oh, and as I said, you don't have to memorize all of this. Really, you should know something about this first measurement. There will be some questions about how the size of the Earth was measured. Okay.